Welcome to lecture 26. This is the first lecture of week 6. In this week, we will talk about unconstant optimization of multivariable functions. In our previous week, we have talked about unconstant optimization of single variable optimization problems. So, we basically have learned about various optimization techniques that are available for optimization of single variable functions. In this week, we will start our discussion on optimization techniques for multivariable functions. So, here the objective functions have more than one decision variables. Like we have classified the several optimization techniques for unconstrained single variable optimization problems into two categories, like direct search methods and gradient based methods. Here also we will classify the optimization techniques that are available for multivariable functions into two categories, direct search methods and gradient based methods. So, in this week we will talk about direct search methods for unconstrained multivariable functions. In the next week, we will talk about gradient based methods for unconstrained multivariable functions. So, in this direct search methods for unconstant multivariable optimization, we plan to talk about at least three methods. They are simplex method, or also known as Nendler-Mead simplex method, Hooke-Gibbs pattern search method, and Powell's conjugate direction method. So, today we will again review the optimal criteria for the unconstant multivariable functions. We introduce the concept of descent direction, take a small problem on descent direction, and we will classify the techniques that we will talk about for unconstrained multivariable functions into two categories, direct search methods and gradient based methods, and we will see what are the methods under direct search method we will study and what are the methods under gradient based methods we will study in this course. So, let us again review briefly the optimality criteria for unconstant multivariable functions. You know there are necessary conditions and there are sufficient conditions. So, we quickly review these necessary conditions and sufficient conditions, and we will take some example problems to understand the concepts better once more. The necessary conditions for x star to be a stationary point of a multivariable function f x equal to f x at x equal to x star are as follows. The function f x has to be twice differentiable, so that you can have information of del f del x at x star as well as del square f del x square at x star. So, both first derivative and the second derivative at x star is required. So, the function f x is twice differentiable. At stationary point, each partial derivative is equal to 0. Thus, each element of the gradient vector of f x at x equal to x star must be equal to 0. So, if you have a two variable function del f del x 1 equal to 0, del f del x 2 equal to 0. So, that is the necessary condition. The Hessian matrix H has to be positive semi definite at x star when x star is a local or relative minimum point. The Hessian matrix H is negative semi definite when x star is a local relative maximum point. So, the necessary conditions are del f del x equal to 0 for x equal to x 1, x 2, x 3 etcetera, and the Hessian matrix is positive semi definite for local minimum and Hessian matrix is negative semi definite for local maximum. Let us look at now again the necessary condition, the sufficient conditions for optimality of a multivariable functions. For a stationary point x star to be an extreme point, that means maximum or minimum, the Hessian matrix H evaluated x star must be positive definite when x star is local or relative minimum point. It is negative definite when x star is local or relative maximum point. If the Hessian matrix is neither positive semi definite nor negative semi definite, the stationary point x star is neither the local maximum nor local minimum, it is a saddle point. So, the sufficient conditions are that at stationary point x star, that means del f del x star equal to 0, at stationary point x star you evaluate the Hessian matrix. If the Hessian matrix is positive definite, then x star is a local minimum, and if Hessian matrix is negative definite, x star is local maximum, and if Hessian matrix is indefinite, you have a saddle point. So, this slide again summarizes the conditions. So, the necessary conditions del f del x 1 equal to 0, del f del x 2 equal to 0 up to del f del x n equal to 0, and this shows the Hessian matrix. Look at the Hessian matrix is a symmetric matrix, and the Hessian matrix is either positive semi definite or negative semi definite. That will be a necessary conditions. But if positive Hessian matrix is positive definite or negative definite at stationary point, that condition is sufficient to say whether x star is minimum or maximum. So, remember the sufficient condition for x star to be a minimum is del f del x star equal to 0 and H, that means Hessian matrix at x star is positive definite, that is sufficient condition for minimum. Similarly, sufficient condition for x star to become maximum is del f del x star equal to 0 and Hessian matrix H at x star is negative definite. So, you have 3 figures indicating local minimum, local maximum and saddle point. Now, let us take an example of two variable function. The function f is a function of x and y, and the function is minus 2 x square minus y square plus 20 x plus 16 y minus 2 x y plus 10. Let us find all the minimum and maximum or saddle point whatever exists for this function. So, basically we find all the stationary points for this function and judge if the stationary point is minimum or maximum or saddle point. So, we start with evaluating delta del f, delta f del x. Delta f del x will be minus 4 x plus 20 and minus 2 y. So, this will be equal to 0. Similarly, del f del y will be minus 2 y plus 16 minus 2 x equal to 0. You can solve these two equations simultaneously. In fact, you can easily solve. You just subtract the second equation from the first one and you will get x equal to 2 and y equal to 6. So, there is a single stationary point, one stationary point at 2, 6. So, to find out if this 2, 6 is maximum or minimum or saddle point, we have to now find out the Hessian matrix. So, the Hessian matrix H will be del square f del x square del f del x del y del f del y del x del f del y square. So, find out these quantities. Note this and this are same. So, if you find out these quantities, del square f del x square, you can find it from here and this happens to be minus 4. Similarly, del f del x del y will be minus 2. So, this will also be minus 2 and del square f del y square can be found out from here, which is minus 2. So, this Hessian matrix is minus 4, minus 2, minus 2, minus 2. Eigenvalue for this Hessian matrix are, if you evaluate, minus 5.2361 and minus 0.7639. So, both the eigenvalues are negative. So, the Hessian matrix is negative definite. If Hessian matrix is negative definite, it means the point stationary point 2, 6 is a local maximum. So, local maximum at 2, 6, that should be the answer. So, maximum at 2, 6. Again, let us find out for this function. So, for example, 2, we take another 2 variable function of x and y. The function is 4 x square plus 5 y square minus 5 x minus 9 y plus 8 x y plus 100. So, again let us find out the first derivative and set that equal to 0. So, let us find out del f del x, which will be 8 x minus 5 plus 8 y equal to 0. Then find out del f del y. If we find out del f del y, it will be 10 y minus 9 plus 8 x equal to 0. Solve these two equations simultaneously, you will get x equal to minus 11 by 8 and y equal to 2. So, you have a single stationary point at minus 11 by 8 and y equal to 2. So, now we have to evaluate the Hessian matrix. The Hessian matrix will be again del square f del x square del f del x del y, same del f del y del x del square f del y square. If you evaluate these terms by differentiating again these two expressions, you will get 8, you will get 8, so 8 also, and you will get 10. The eigenvalues of H are 0.9377 and 17.0623 if we evaluate it. Both the eigenvalues are positive. It means the Hessian matrix is positive definite. So, Hessian matrix is positive definite means x equal to minus 1 8, y equal to 2 is local minimum. So, the stationary point is a minimum. So, you have a minimum at minus 11 by 8, 2. So, let us take the third example. Again you have a function of two variables minus x square by 2 plus 2 y square plus 20 x minus 5 y. So, again let us do the same thing. We have to take del f del x, we have to take del f del y and set those equal to 0. So, if I take del f del x, it will be minus x plus 20, which I set to 0, and del f del y will be 4 y minus 5 equal to 0. So, this is straightforward to solve. X equal to 20 and y equal to 5 by 4. So, again you have a single stationary point at 20, x equal to 20 and y equal to 5 by 4. To understand whether this stationary point is a minimum or maximum or saddle point, we have to now consider the Hessian matrix. So, again let us take the Hessian matrix. Del square f del x square del square f and del x del y del square f del y del x del square f del y square. So, if you evaluate this, it will be minus 1 and then 0. So, this is also 0 and this is 4. So, here for this example, the eigenvalues are basically the diagonal elements. So, the eigenvalues of H are equal to -1 and 4. So, one eigenvalue is negative, another eigenvalue is positive, those show the Hessian matrix is indefinite. So, if the Hessian matrix is indefinite, we know that the stationary point is a saddle point. So, we have a saddle point at x equal to 20, y equal to 5 by 4. Okay. So, now let us introduce the concept of descent direction. Let us consider the unconstant optimization problem, minimization of f x. At any kth iteration, the next point is given by x k plus 1 equal to x k plus alpha k d k. You can consider x as vector. So, what is told here is basically is as follows. So, if you have a point during your iterative search and you want to find out the next point, we can decide a direction and then move certain steps along this direction. So, maybe I will move up to this. So, x k plus 1 is this, which is obtained from x k by adding this much along the direction as shown. So, if d k is the search direction and alpha k is the step length at kth iteration, the next point at k plus 1 iteration can be obtained as x k plus 1 equal to x k plus alpha k into d k. So, d k is the search direction and alpha k is the step length. If d k is a descent direction, then the function value at x k plus 1 will be less than the function value at x k. That means, if d k is the descent direction and if you are moving along that direction, the function value will decrease. So, f of x k plus 1 is less than f of x k. Now, x k plus 1 is x k plus alpha k d k. So, you can also say f of x k plus alpha k d k is less than f of x k. Now, I can expand f of alpha k, f of x k plus alpha k d k into Taylor series, and if I do that, by Taylor series expansion you can write f of x k plus alpha k d k as f of x k plus alpha k into gradient of f at x k dot d k. So, the Taylor series expansion of this can be written as this. So, from both sides we can drop f of x k and then we see that alpha k into delta f into gradient of f dot dk is less than 0. Since alpha k is positive, we see that the gradient of f at x k dot dk is less than 0. So, if dk plus, so if dk is descent direction, the dot product of dk with the gradient of the function at x k will be less than 0. So, this is the condition for the descent direction. So, the condition for the descent direction is that the dot product of the gradient at x k with the descent direction is less than 0. So, if I am given a direction and I say, and if I ask that I have a given function, tell me if the dk or if the direction given is the descent direction at a certain value of the function. All we have to do that, we have to take the gradient of the function evaluated at that point and take the dot product of that with the direction. If this dot product is less than 0, then the given direction is descent direction. So, when the if the dk is descent direction, this condition must be satisfied. The dot product with the gradient of the function at x k with dk is less than 0. So, let us take a simple problem so that you can understand the concept better. So, can consider the two dimensional function 2 x 1 square plus x 2 square whole square. Show that v equal to minus 1 0 is the descent direction at x 0 equal to 0 1. So, x 0 equal to 0 1, we have to find if the direction minus 1 0 is the descent direction for the function f at x 0 equal to 0 1. So, that is the question. So, the question is this direction v equal to minus 1 0 is the descent direction of the function f x at x equal to 0 1. So, what will you do? I will evaluate the gradient of this function at this x 0 point and then take the dot product of that with v, which is the direction. If the dot product is less than 0, the v is a descent direction. So, I find the gradient and v is the descent direction if the dot product of the gradient of the function with v is less than 0 at x 0 equal to x equal to 0 1. So, the gradient at 0 1 is 4 4. Now, find the dot product and the dot product is minus 4, which is less than 0. So, v is the descent direction. So, this is how we can find out if a given direction is descent direction or not. So, now we will classify all the unconstant multivariable optimization techniques that we will talk about in this course into two categories as direct search methods and gradient based methods. And under direct search methods, we plan to discuss Nelder and Mead simplex search, Hook and Jeeves pattern search and Powell's conjugated direction search. This will cover in this week. In the following week, we will talk about gradient search, gradient based methods. So, these methods will make use of gradient informations, and the direct search methods will make use of only function value information. So, the gradient based methods that we will discuss during the course are Cauchy's method or the steepest descent method, Newton's method and Marquardt's method. So, in the next lecture, we will talk about Nelder and Mead simplex search method. With this, we will close this lecture here.